Good afternoon, everybody, and thank you for your interest in attending this small talk about the groundwater hydrology of springs, which I've been invited to give by the British Hydrological Society. And I would like to mention also that that is in the context of World Water Day, which is next Tuesday, the 22nd. The theme of World Water Day this year is groundwater, making the invisible visible. So I thought it was quite apposite to choose the subject of springs, the point at which groundwater does indeed come to the surface. I'd also like to mention the International Association of Hydrogeologists. If you're not aware of them, they're a fantastic resource for all sorts of information about groundwater. They have numerous commissions and groups working on different aspects of hydrology, from climate to development to thermal waters to karst, and so on and so forth. IAH.org, simply enough, just look them up on the web. Okay, so without further ado, the theme of World Water Day, groundwater making the invisible visible. And if you go to their website, you'll find this nice picturesque graphic and a few of their strap lines and talking points. And I've selected two of those talking points to just mention a couple of things. And the first one sort of explains the meeting title to a degree: where is all the water? Now, as we all know, the majority of the fresh water in the world is groundwater, but we don't really pay much attention to it a lot of the time. And there are these other aspects of it. For example, the buffering capacity for climate that groundwater offers is very high, and we need to be able to think about it in the context of our catchment science. And we need to be able to incorporate thinking about groundwater into our general hydrological understanding of how hydrological systems work holistically and interacting with the biosphere, the atmosphere, and so on. So this is really a sort of a call to work interdisciplinarily with your colleagues in groundwater and vice versa. Okay, so we're going to start out just with these sort of headings basically form the structure of the talk, really. And it's about how to classify springs according to discharge rate and uniformity, the geology and geomorphology controlling discharge, the character of hydraulic head forming the springs, and I have a few words on water quality and temperature. Now, there's a logical sequence there that will become apparent as we go through the talk. The bulk of it is going to be on the second and fourth items there, but just to characterize the size of springs and what we're talking about in the UK. This is a 1923 definition from the United States Geological Survey, and there's a few early references to early works in this talk, because often the classics of hydrology have stood the test of time. Mine's is one of them. And here we have this definition of the magnitude of spring discharges. And in the UK, we don't have anything in the first magnitude there. And we have some springs in the second magnitude, the largest of which I'm aware is the public water supply, the springs that are used for public water supply down the Chalk haven't, which is there. It's at the bottom of the range for the second magnitude of spring. Now, on the right-hand side, we can see the indices of variability, or measuring variability, measures of variability of spring discharge. And the reason that this is important is because it can tell you a lot about the structure of the ground, the structure of the permeability of the rocks that are supplying water to a spring. And whilst it can be quite difficult to get insight into the ground, drilling boreholes is expensive, they're typically few and far between. Quarries give you some limited access to looking at the rocks and so on and so forth. So there's, in geology, there's a lot of inference, and springs contain an abundant quantity of information about catchment processes and about the ground. So I'll expand on that a little with a basic overview of some types of flow in the ground, which is necessary for understanding spring discharge. Now, we have the graphic from the UN here, and it really shows sort of a gravel aquifer, you might call it, which is comprised of lots of particles, fairly uniform, and sort of a fairly uniform distribution of pore sizes and probably a fairly uniform permeability throughout. Now, the storage characteristics are relatively uniform, and the permeability characteristics are also relatively uniform, such that the drainage from a spring sourced by such a geological formation might be expected to be of low variability. On the top right, we have a bedrock aquifer, and here we can see lots of fractures and joints, and it might not necessarily be a particularly good aquifer. It could be a crystalline basement rock, such as Louisian gneiss or granite, and it could be then fed by storage within the regolith, which looks more like this sort of storage down at the bottom, and it might have, we have to consider the relationship between the storage component and the permeability component, because the permeability component controls how rapidly the drainage occurs. If drainage is occurring through fractures, these will be relatively high permeable features, and if it drains through pore spaces, these will be relatively lower permeability features, but with higher storage. So some rapid flow could be sustained through here. If we compare this to a karst aquifer, this is a limestone aquifer, such as the Carboniferous limestone in the White Peak in Derbyshire, which people will be familiar with. This is a limestone that has a crystalline matrix and very low storage, but it's soluble. And the conduits that form within it are of extremely high permeability, so that there's a small amount of water held within the aquifer and it drains very rapidly. This means that it responds very rapidly to rainfall. So the water tables go up and down rapidly, and spring discharges are highly variable. Here are a few schematics of spring settings in different geological contexts, and I'm going to talk about some of those in a little bit more detail in the following schematics. So geological barriers cause groundwater, flowing groundwater, to come to the surface. And here are a number of settings in which that occurs. For example, here we have two different lithologies faulted against one another, and water flowing through the one encounters the barrier and then discharges at the surface at this point. A similar setting is here, except the barrier is imposed by an intrusive volcanic dike. Here we have an aquifer that is confined, that is, this is the porous material and it has an impermeable layer above it. It is faulted, and at that point, the pressure which is being driven from up gradient in the ground forces the water to the surface. And here we have similarly a confined aquifer, but it reaches its outcrop with the flow driven with the head from here. So those are typical geological settings. Here are some more. This is the cutest type of spring name that you can encounter, the dimple spring. And these are types of what are known as depression springs. And it's basically where you have a relatively uniform geology, but the water table intercepts the surface of the land. And these are some typical settings in which that occurs, such as a small erosive feature. It might be due to perhaps some sort of minor difference in the hardness of the bedrock, or glacial action or something, causing the appearance of the water table at the surface. And here, the typical setting in a valley, and that's mirrored here. That's a sort of a wider view of this type of setting. Contact springs, we're starting to involve a little bit more geology in a contact spring, and often these appear where we have a permeable deposit layered over the top of an impermeable deposit, and the springs appear at the junction of the two deposits. And we can see a couple of different examples here. Obviously, this is an American example. And here we have a perched water table over, possibly, for example, in the context of Northern England, this might be a glacial clay overlain by a fluvio-glacial sand and gravel, and you may have discharge from a perched water table, controlled by the position of the low permeability strata. And if you were to tilt it all up, thanks to plate tectonics, Brian in 1919 had his eye on this. You have similar settings, but it might affect the distribution of the actual spring to the down gradient side of the topographic feature. I've mentioned karst springs. Karst springs are prevalent in throughout the world. Something like 20% of the surface of the terrestrial surface of the Earth is covered by carbonates, principally limestones, which are soluble. And we have often you have them abutting sandstones or other non-soluble rocks, which generate runoff, which go down sinkholes and accumulate in a hierarchical drainage network, which often culminates at springs. And an example from the Yorkshire Dales here is at Malham Cove, and the spring at Malham Cove. And we can see here we have the millstone grit, which forms Fountains Fell, underlain by the sort of marley limestones of the Yoredale beds, generating surface water flow. And as soon as we get to the Great Scar limestone, the water disappears, it sinks underground and feeds Malham Tarn, which appears on the Silurian slates, which underlie the whole lot, before sinking again beneath Watlow's Dry Valley to emerge at Malham Cove. I'm sorry, I've not been able to find the correct citation for this diagram, which I had in my records. I've put down some likely candidates there. Okay, so that was a sort of a brief overview of the types of geological setting in which you might find springs. And I want to briefly touch on the character of the hydraulic head forming a spring. We've mentioned confined aquifers. So we can characterize discharge as driven by gravity, which is that we reach the head is just driven by gravity in the unconfined setting, causing discharge by the water being above the point of discharge, whereas in the artesian setting, whilst gravity is obviously still fairly important in this setting, it's the pressure which drives the spring to come up, and famous for Artois. And this is what we've seen. We can combine these different types of classification, the character of the hydraulic head with the geological setting. And I want to mention one other, which is the hydrothermal hydrothermal convection springs with some examples from the UK. I won't go into too much detail in these, but essentially we have settings in which cold water is sinking, is becoming heated at depth, and as it becomes more buoyant and hotter, it starts to rise to the surface, and the convection is the principal driving force, coupled also with some topographic drivers such as at the Bath Hot Springs and elsewhere. And if we look at these are the main hot springs in England, and we can see that almost all of them, in fact, are in Derbyshire, with these Bath and Bristol hot springs down there. So I've got 5 minutes left. I want to talk about water quality and temperature. And in the same way that measuring the discharge at a spring, which is a straightforward thing to do, can provide a lot of information about the structure of the permeability of the rocks behind and beneath and feeding the spring, the water quality and the temperature contain a great deal of information about the history and the provenance origin of the water sourcing the spring. Now, if we imagine this is a spring rather than a river, we can see that the water feeding the outlet is an amalgam of multiple flow paths, all of which have different lengths and different residence times. So when we measure, we can use various tracers, radionuclides, CFCs, tritium, so on, to determine residence time distribution, and that information can tell us about the origin of the water. I would say the first port of call, though, is the basic chemistry. Is the major ion chemistry and possibly some minor ion chemistry. And I want to talk about the relationship between flow path length, residence time, and water quality. We're all concerned with water quality. It's important to recognize that water quality is a function of all the processes occurring upstream of the sampling point, whether that be a surface water or a spring. And springs can tell us a lot about the nature of the flow paths. Now, this is a basic model, say, of a uniform porous media with flow entering into the top of the hill and being discharged to a valley, a watercourse or other outlet. Now, if we magnify that up to a regional scale, and you can see this is an American diagram, but we have several kilometers in scale and several thousand, a few kilometers in depth, like 3 kilometers or so depth. We can see that we have the superposition of local, where this arrow here, where does this arrow go? You've got flow that just goes straight down. Well, that's something like down here. So these are very long flow paths. And in a discharge area like this, numerous flow paths converge from different recharge areas. And this is in a regional context. Now, the reason that is important is because we have hydrochemical evolution along the length of a flow path. And these local, intermediate, and regional zones are characterized by greater or lesser degrees of flushing of the bedrock and greater or lesser degrees of dissolution of the minerals which comprise the rocks. And when we look at the water chemistry of a spring, we can tell how the regional, local, or intermediate flow systems are interacting. And here's a summary diagram from Toth 2009, and he brings in various processes which culminate. We have short flow paths here, culminating in freshwater springs, and we have longer flow paths here with increasing, with changes in the dominant dominant anions, changes in the total dissolved solids as more and more rock is dissolved, changes in temperature, and how these can lead to changes in the vegetation and changes in water chemistry at the surface. My time's just about up here. I hope that was useful. We have I mentioned in the abstracts of the talk these chalybeate springs, and I've managed to find one of the funniest quotes about chalybeate springs, which is that these waters can cure you of the colic, the melancholy, and the vapours. It may lean the fat lean, killed flatworms in the belly, loosened the clammy humours of the body, and dried the overmoist brain. So you can find if you feel you're suffering from an overmoist brain, and you happen to be in the Pennines, you can go to this chalybeate spring. I don't know if you can get in, but or else if you're in the south, you can go to Tunbridge Wells. But there's many of these. Thanks very much.